All right. So when we talk about intermolecular forces, we're talking about uh, like forces that are between molecules. I don't know why this is taking so long to. All right. Can everybody see my screen?
Yes, sir.
Yes.
Okay. All right. So forces between molecules. So you basically have four types of intermolecular forces that we're going to talk about. Right. You have ionic. I'm going to say attractions or interactions. Right. Like a lot of times you'll hear the term, you probably heard it in CHEM, of something like an ionic bond, but it's not really a bond because there's no electron share. It's really just an attraction. So if I have something like sodium chloride, where sodium is positive and chlorine is negative, bless you, right? There's no shared electrons here, right? It's only the charge is keeping those two with each other, right? One is positive, one is negative, and so they attract one another. There's no shared electrons. But this is also the strongest it's the strongest IMF out of all four. Right? So there's no shared electrons, just different charges. One's positive, one's negative. Boom, they find each other, they love each other, and they hang together. Right? That's going to be really important to understand when we start doing acid-base chemistry, because a lot of your bases are salts. But I don't want to get too far into that. But a lot of times your base will be a salt, and then your conjugate base from the acid is also going to be negative, so that'll be a part of a salt too. But we'll talk about that shortly. I think that's the next section, if I'm not mistaken. So you got ionic attractions, and then the other three are specific to covalently bound molecules. So you have what's called van der Waals. How many of you have heard of this before in GChem?
I have.
I have.
All right, cool. So we're not just van der Waals forces. Sometimes you'll hear them called London forces, right? London forces, everything experiences this. Right? And we're going to talk about like that. I'm going to pull up another document and we'll discuss like what that looks like and how it happens. If you saw the video, then you saw it already. I'm just going to recap it and then we're going to start working some examples. Right? So everything experiences London forces. This happens to be the weakest. Right? This happens to be, excuse me, the weakest of all your intermolecular forces. Right? And then you have dipole interactions. Right? That's one intermolecular force. And then you have hydrogen bonding. Right? And this is the strongest out of your covalent intermolecular forces. All right? Any questions about that? So you have dipole, well, van der Waals, dipole, and hydrogen bonding. Those are your three, and that's in order of strength. So the weakest is van der Waals, and then dipole, and then the strongest is hydrogen bonding. All right. So when we talk about intermolecular forces, we're talking about, again, if I have, let's say I have a molecule of heptane, right? The van der Waals forces and or hydrogen bonding, or there's no dipoles here, but the van der Waals forces that this experiences is going to be between itself and another molecule. Oh, I'm in class, Jen. Did you hear me? Don't answer it. Then nobody should be at the door. It's 11 o'clock, and I didn't order nothing. All right. Okay. Bye. Love you. Sorry. Homeschooling. Who's at my door at 11 o'clock, though? I should just go slap them just for coming. It's the wrong time of day. So let me go back to here. So intermolecular forces are experienced between molecules. So when you're talking about intermolecular forces, or whether it's dipole, van der Waals, or hydrogen bonding, you're talking about between two of the same thing, right? So if you have a flask full of heptane, or a flask full of acetone, or a flask full of water, those forces are going to be between molecules. So here, this will be strictly van der Waals forces, right? If I had acetone, right? This would be, so acetone is here. And if you remember when we talked about dipoles, the oxygen here is partially negative, the carbon is partially positive. So on this oxygen, this is partially negative, and then this carbon is partially positive. So in a molecule that has a dipole, those molecules are going to line up so that the positive parts and the negative parts see each other. Right, so the negative, partial negative oxygen is going to line up so that it sees this partial positive carbon, right? So this is the thing to remember, is that although the dipole is a specific intermolecular force, this also experiences van der Waals, because every type of molecule experiences that. All right. Any questions about anything so far? We're gonna look at some examples to make this make sense.
So the van der Waals is based on the dipole moments that you have in each molecule.
So basically, the way you think about that, and I'm gonna pull that up too, that because I know that was on the slide in the video. But the way you think about it is like you have these little micro dipoles, even though, remember we talked about bonds being polar covalent and non-polar covalent?
Yeah.
So if we have, let's say this CH bond right here, even though it's not a polar covalent bond, there's still some polarity. Be partially positive, carbon be partially negative, because there's a slight difference in the electronegativities of the atoms, right? So imagine that being basically spread over this whole molecule, because you got CH bonds throughout the whole thing, right? So you'll have that. So it's kind of almost like a, how do I put it? It's similar to the electrostatic attraction, but it's not as strong, right? Because all these little partial micro dipoles throughout the whole molecule, they do add up, right? And so you have another molecule another of the same molecule that comes in. They basically try to line up to find the difference in the charges. So the positive is going to line up with the negatives.
Okay.
Yeah, that's a great question. So it's based on partial dipole. I wouldn't say it was a full dipole moment because the electronegativity difference is too small, right? So these are not polar covalent bonds. But the dipole is based on a polar covalent bond, right? So that's why that's a little bit stronger interaction. And then the other covalent intermolecular forces is hydrogen bonding. This is a very strong interaction, right? So you know there's a dipole here where H is partially positive and oxygen is partially negative. And then another oxygen from another of the same molecule. Keep in mind, we're talking about intermolecular forces, right? So you got another molecule that's coming in and that's in the same flask. And the lone pair on that molecule is going to be attracted to this partial positive on hydrogen. Right, so that lone pair, let me redraw this to make it make more sense. That lone pair on that other oxygen, you're going to have an interaction between it and the hydrogen. So that's the essence of hydrogen bonding. Right, you'll have a lone pair on an atom that's attracted to a partially positive hydrogen in another atom. I'm gonna draw it this way. Right, so let me write that down. So your lone pair here is attracted to H. Right, so that lone pair is attracted to hydrogen. Right, and so hydrogen bonding is a really strong interaction. And when you think about hydrogen bonding, the best example of how strong hydrogen bonding is in DNA, because that's the intermolecular force that holds DNA together. Yep. Have you ever, how many of you have seen that double helix in DNA? Right, you have a kind of a helix, a double helix like this, right? The attraction between the two sides in the helix, because each helix is made up of a different strand of amino acids. That attraction comes from hydrogen bonding, right? So it's really the fact that it's the strongest intermolecular force is a testament to the fact that I don't know what you believe in, but there has to be a creator somewhere. Because imagine if DNA was held together by van der Waals forces only, we'd be up the creek. Our DNA would be like spontaneously unzipping all day, every day. So let me go to another. Let me go back to here. All right, can y'all see that?
Yes, sir.
Okay. All right, let me go back to here and so we can look at these illustrations. Because I know this was in the video, but I'm just going to recap it, right? So if you look at the van der Waals, can y'all see the different charges, how on just any given molecule, in this case, they use pentane, right? And the strength of that intermolecular force